great, thanks. Let's see. So yeah, so the general theme of what I want to talk about today is how ideas from tropical geometry can be used understand to understand intersection theory of certain interesting moduli spaces. So the starting point for this work is really on understanding compactifications of complements of hyperplane arrangements. So the setup here is so I have a a I have a variety y which is the complement of n distinct hyperplanes in a in a in a affine space, or I could also do it with projective space. And uh, and then what I would like to do is find a compactification of y that that is described by some sort of combinatorial data. And the data that I am interested in is encoded in what's called the tropicalization of y. So this is some fan or some support of some fan in r to the n, and there's lots of different fan structures that you can take on this fan. So I so I wrote down one fan structure that essentially encodes all of the information about how these different hyperplanes intersect. But the particular fan structure is not so important for me. The point is can I can I can associate to this variety y its 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 uh its tropicalization, which is some support of some fan, and then I can use this tropicalization to try to find good compactifications of this variety y. So the main theorem about these compactifications I've written down here. So it says if I take any unimodular fan structure on this on this tropicalization, so this gives me a smooth toric variety, and this gives me and then what I can try to do is take the closure of y in this smooth toric variety, and then what this theorem says is 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 that when I do this, then I am actually going to get a a a a good compactification of y. So this closure y bar, it's going to be smooth and proper, and then this toric variety x sigma. So this is stratified by torus orbits, which correspond to the cones of this fan sigma. and and then the second condition here just says that that these that this stratification of this toric variety pulls back to to a nice stratification of this compactification y bar as well. And then the last property that I'm most interested in is this third one that says the Chow ring of this compactification y bar is the same as the Chow ring of this toric variety x sigma. So what I would like to do is explain why we have this isomorphism here, and how we can generalize this and use it to describe the Chow rings of certain compactifications of moduli spaces. But before I move on to that, I guess that I should probably mention, so I didn't write down who this theorem is due to. So it's kind of due to lots of different people. So this third part here, the most um, self-contained exposition of this is in a paper of Gross from 2015, and these two parts here, so they uh, so it kind of can be attributed to a number of people, but the perspective that I am most interested in comes from work of Tevelev on tropical compactifications. Yeah, so what I want to do now is try to explain why we have this isomorphism of Chow rings in this third part here. So there's basically there's two different aspects to this. So I guess I'll right here. So I have this inclusion of y bar into this toric variety into this toric variety x sigma, and this gives me a pullback of the Chow rings, and I'm going to describe some very simple conditions that ensure that this pullback is a bijection. So the first condition is the fact that if I take any unimodular fan that is supported on this tropicalization of the complement of a hyperplane arrangement, and this fan is going to be what's called a Poincare fan. So what this means is so this is a d-dimensional fan in R to the n, and there's sort of a natural way to get a degree map from AD of x sigma to z, and the way that this works is first I'll pull back a cocycle on x sigma to AD of y bar, and now that is a complete variety of dimension d, so I'm going to have a degree map there. So then I can look at this composition here, and the statement that sigma is Poincare says that this composition gives me an isomorphism of AD of x sigma with z, and if I do the same sort of composition for for all k, then I'm going to get this commutative diagram here, where this top arrow is an isomorphism, and this implies, since this is an isomorphism, that this pullback map is injective. So the statement here is that sigma is a Poincare fan of dimension d. So even though x sigma is not a complete toric variety, it behaves as if it were a complete variety of dimension d, and this induces a injective pullback map to the compactification y bar. So that's how we get injectivity of this map, and then for surjectivity, so the key observation here is if so I had this stratification of my toric variety by the torus orbits, and I pull that back, and I get a stratification of my compactification y bar by the intersections with the torus orbits, and it turns out that each of these strata is itself a complement of a hyperplane arrangement. So then this gives a sort of like recursive description of the strata of this compactification, but in particular, it implies that the Chow groups of y bar are generated by the classes of the closures of these torus orbits. which in turn implies that I star is surjective, because the Chow groups of the toric variety are 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 also generated by the classes of these torus orbits, which pull back to the classes of these strata of Y bar. So maybe I'll say a quick word about why the fact that these strata look like complements of hyperplane arrangements imply that these Chow groups are generated by the closures of these strata. And the idea is very simple. So if I have a complement of a hyperplane arrangement, then I can basically, so I've basically written it down here, but I get this exact sequence here, and then I can just compute from this exact sequence exactly what the Chow groups are, and I see that they're basically that they're that they're that they're basically trivial, so they vanish except in degree equal to the dimension of y, in which case they're just going to be equal to z. So this condition implies that if I if I have a stratification of 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 a variety by strata that take this form, then the Chow groups are generated by the classes of the closures of these strata. So I'm just going to give this a name and say that these Chow groups, or that these varieties where the Chow group looks like this, I'm going to say that they are Chow free. So this essentially describes why I get this isomorphism of Chow rings that I mentioned up at the beginning. So the point is, one, this fan is Poincare, which ensures that we have an injective pullback map, and two, these strata also look like complements of hyperplane arrangements, which implies that we have a surjective pullback map. So that's what the situation is for compactifications of complements of hyperplane arrangements. So now what I would like to do is discuss how we can generalize this to to certain settings which are not necessarily compactifications of complements of hyperplane arrangements. So now instead of taking Y to be a complement of a hyperplane arrangement, I'm just going to take Y to be any closed d-dimensional subvariety of an n-dimensional torus. And again, I can associate to Y a combinatorial object called its tropicalization, and it's not so important for me what the definition of the tropicalization is. The important point is that it is support of some d-dimensional fan in R to the n, and then I can again use this to try to find compactifications of Y. So I'm going to do basically the same thing. So I'll take a fan structure on this tropicalization, and this is going to give me a toric variety with torus T. So that gives me a partial compactification of this torus T, and then I will try to compactify Y by taking its closure in this toric variety. And if this closure behaves the way that we expect it to, then it's called a tropical compactification. So this means that Y bar is proper and that Y bar intersects the torus orbits in the expected dimension. So this notation here, I should mention, is due to Tevelev. So the question then that I am concerned with is, when is the Chow ring of this toric variety the same as the Chow ring of Y bar? so the first thing to note is that this can fail like pretty easily. So I've written down an example here. So if I just take any projective variety whose Picard rank is at least 2, so this is a tropical compactification of its intersection with with a standard torus in projective space, but but we cannot have an isomorphism of Chow rings here, um, because the Picard rank on the left is 1 and on the right it is at least 2. So the the property that the Chow ring of this tropical compactification is the same as the Chow ring of this torque variety is somehow very special. And what I'm going to do now is give a criterion for these Chow rings to be the same, and the criterion is basically exactly what I wrote in the case of the complement of a hyperplane arrangement. So I so so I showed you there that if the fan is Poincare, then we get that the pullback map is injective, and if all of the strata are irreducible and Chow free, then the pullback map is going to be surjective. So this gives this criteria for these Chow rings to be the same, which the way I've written it makes it essentially a trivial statement. So so the so the really the really interesting part here is finding criteria to determine like when this fan sigma is Poincare and when these strata are all irreducible and Chow free. So I'm not going to get into a lot of details on this just because it's not what I want to focus on, but it, it gets into very interesting concepts in tropical intersection theory. For example, instead of showing these two properties separately, in most cases it is actually easier to instead show some stronger facts about this fan sigma, such as both sigma is Poincare and all of its different star fans are Poincare as well. And that in turn is going to give you information about the strata of this compactification. So in most cases, it really turns out that that the best way to prove these conditions is to instead prove something stronger, which implies both of these conditions, and therefore automatically implies that the Chow rings are the same. So one particular example where this works is when y bar is the compactification of the complement a of of a hyperplane arrangement, and this theorem allows me to determine similar results where y bar is a compactification of not necessarily an arrangement of hyperplanes, but maybe of some hypersurfaces. So instead of going into more detail about that now, what I would like to do is is to describe some applications of this work to Chow rings of compact moduli spaces. So the first the first example here is really this theorem due to Kuehl from the early 90s, which in my view is really like the first result on Chow rings of compact moduli spaces. So what this says is that the Chow ring of the moduli space of stable in-pointed rational curves. So this is generated by the classes of these boundary divisors, and then and then the only relations here are sort of the obvious ones that I've written down here. So if you're familiar with what the chowering of a smooth torque variety looks like, you'll see that this basically looks like the chowering of a smooth torque variety, and in fact, there's a very good reason for that. So the reason is, if I just look at the interior, which is just the locus of endpoints on P1. So I can fix the last 3 points at 0, 1, and infinity, and then I can scale the equations for the remaining points, and I'll get these coordinates on m0n described by this matrix, which embeds m0n into a to the n minus 3 as the complement of the 2 by 2 minors of this matrix. So as a complement of this arrangement of hyperplanes here, and then and then it turns out that m0 n bar is the compactification of this complement of this hyperplane arrangement associated to the minimal smooth fan structure on its tropicalization, and then this immediately gives this presentation of the Chow ring here. So what this does is it gives a theoretical understanding of this theorem due to Kuehl, which he originally proved by a number of very involved computations of Chow rings of blowups. So with these techniques, we don't need to do those difficult computations. We just immediately have this. So this makes these methods very enticing for generalizing to more complicated moduli spaces. So what I would like to describe now is how we can apply the same sort of techniques to describe Chow rings of moduli spaces of higher dimensional varieties. So the first such moduli space that I'm concerned with is the moduli space of moduli space of hyperplane arrangements in projective space. So this has a natural modular compactification due to Hacking, Kuehl, Tevelev, and separately by Alexeev, which is basically the natural higher dimensional version of of M0 and bar. So it can be described as the closure of the space MRN and some particular toric variety here. I'm not going to describe what this toric variety is, but it's very complicated, and this compactification here, it is usually not going to be a tropical compactification. So it's really only tropical in these special cases that I've written here, when R is 2 or when R is 3, and when n is less than or equal to 7, or conjecturally less than or equal to 8. And it turns out that in these cases, where this compactification is tropical, we can use the results that I've discussed above to describe what the intersection theory is. So the theorem here is that if I take a unimodular fan structure on this tropicalization of this moduli space of hyperplane arrangements, then this is going to give me smooth a smooth tropical compactification, and the Chow ring of this compactification is described by the Chow ring of the toric variety. So this does not quite describe the Chow ring of the of 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 the stable pair compactification, because that compactification is not smooth in general. But what it does describe, for instance, is the Chow rings of this of this of the small resolutions of this of this stable pair compactification. Um, so that so it is currently ongoing work to see how much we can generalize this 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 theorem here to the remaining cases. But instead of doing that in the last couple minutes, I would rather discuss another related moduli space, which is in some senses much easier to understand. This is the moduli space of Mark del Pezzo surfaces. So the way that this works is instead of looking at hyperplane arrangements, I'll look at point arrangements, and then this is going to be contained in the space and contained in the moduli space of hyperplane arrangements by projective duality. And if R is 2, then they're going to be the same, because I'm just looking at points in P1. And if R is 3 and n is less than or equal to 8, then this space can be identified with the moduli space of Mark del Pezzo surfaces of degree 9 minus n, just by taking the endpoints in the plane and then blowing them up. So this is another natural generalization of the moduli space of the moduli space M0 and R, and it also has a nice compactification, which was constructed again by Hacking-Keel and Tevelev. So I'm low on time, so I won't go into the details of this compactification. I will just note that it is a smooth tropical compactification, and it is described as the closure in some certain toric variety, which is very explicitly described. So they do this for n less than or equal to 7, but I think that it probably works for the remaining case. N is equal to 8 as well. But the point here is in these cases where this compactification is known, the techniques that I've mentioned basically immediately give this very straightforward presentation of the Chow ring of this compactification, which is really the natural higher dimensional version of Kuhl's presentation of the Chow ring of M0 and bar. So that's one of the main applications of these techniques, and I hope that they can be applied to many more examples of compact moduli spaces, but I'll stop there.